people who didn't get to come. Alright, so I posted my worksheets, I think yesterday. I'd read on it the day before, but I'm going to be going over worksheet 19, which is a lot of stuff that I talked about during, like after I finished the worksheet last week, so it's just a bit more review of some stuff, I guess. Okay, so the question for number 1 says that the following reaction, like the product here, is not the only monohalogenated product. So when I say monohalogenated, I just mean only one halogen was added. We didn't have 2, and if we had 2 added, it would probably look like this with the 2 halogens on the same thing, but that's not what we're looking at. So I just asked to draw the other products that form, identified a major product, and I didn't ask to explain why, but that's kind of important too. So there's, thank you, Johnny. So there's like this carbon, this carbon, this carbon, this, and this. Like the halogen can add to all of these. So that's really all there is to the problem, just drawing the halogens getting added to the various carbons. So there's 1. Thank you, everybody. So these are all the products. These 2 are the same thing, because well, if you were to name this molecule, you'd name it the same way. Just to go over it quickly, it'd be like 1-chloro, 2-methyl butane, and it would be the same if you named this one. So these are the same. So if you were drawing all of these for this kind of problem and you drew both, then he might mark you down. I don't know if he'd be asking drawing questions, but in the event he did, just be aware that drawing the same thing twice usually isn't good. And this would be the major product for this, because like an intermediate in this reaction with H nu, oh, that should go on the bottom, shouldn't it? So Cl2 and H nu is a radical reaction. So an intermediate will be a radical that combines with a chlorine radical like this to lead to, in that case, like this product. And the intermediate for this major product that I've circled is this radical, which is tertiary. And because it's tertiary, it's the most stable radical compared to if it was here, that would be primary. And here it's secondary. Those 2 are also primary. So that's the reasoning for number 1. Hopefully that makes sense. Okay. Number 2 is looking at the allylic bromination reaction. So this is one of 2 reactions you guys know with NBS, and you should know that NBS is just a source of Br2. And H nu is just light, which you see for radical reactions. So for this reaction, there's this position and this position that are allylic. They're right next to the double bond, but these are both the same. So you really only have to look at one of them. You could draw both, but like if you named the product, it would be the same name if you put the bromine on the top or on the spot to the right. So you only have to draw one. So if the radical formed at the top, you'd get this monohalogenated product. And to get to the other product, you can like draw the intermediate species that forms just to kind of help guide you. So like this is the radical that leads to that bromine product. And then because it's right next to a double bond, there's this resonance form. So then the double bond is here and the radical is here. And then this would lead to, like the bromine would add to this radical to get a product. So it would look like this. So these two with the bromines are the products. And well, this radical here that led to this product is secondary. And this radical doesn't look very good. It's primary. I might have given you some misinformation last week, and I don't even know if your professor is going into this much detail, but in the event he is, when you're trying to determine the major product for these, you should look at both the radical stabilities, like primary versus secondary and tertiary, and they should all be allylic, so that's not relevant, but like the substitution, but also look at the alkene stability. So this alkene has two substituents on it. There's 1, 2, so it's disubstituted. But this alkene here that we got from the resonance form has 3 substituents, so it's trisubstituted. And alkenes follow the same substitution stability pattern as cations and radicals and everything. The more substituents an alkene has, the more stable it is. So because that alkene has 3 substituents compared to this one that had 2, this is the major product for this reaction. So that's just going back to the alkene stability trends. Hopefully that makes sense. So if there were 2 things that had like alkenes with the same number of substituents, but then the radical had a different substitution pattern, then you'd look at that. But I believe the alkene stability takes priority because that's what persists in the product. So that's what's more important. Okay, so for this, there are 2 allylic positions. There's this one and this one that are right next to the double bond. So we can just start by drawing like halogens getting added to those allylic positions. We don't really have to show anything to get there. So these are 2 of the products. And then some intermediates that form. This radical here has a resonance form with the double bonds, just like any other allylic radical. So now we have this radical here, and that leads to a product, which I'll just go ahead and try to save space. The bromine goes where the radical just was, like this. Okay, I'm gonna circle all the products because I'm running out of space. Just because it's getting a bit cluttered. So what I'm circling is the products, and I'll point out the major one at the end. The other allylic radical that can form is this one. And then we have this resonance form. So now the radical's here. And if a halogen added to where that radical is, then we'd get this product. Don't worry about it. Thank you for coming. Okay, so the 4 products I have circled are what form. And again, we should look at alkene stability first before looking at the radicals. So these top two, there's two substituents on the alkene. So it's di-substituted up here. And then this one as well, things I'm kind of highlighting are the substituents on the alkene. This is also di-substituted. And then this one, the last one I drew, has 1, 2, 3 substituents. So it's tri-substituted. So because this alkene has the most substituents, it's the most stable alkene. So that is the major product because of the alkene stability. So this is the major product. And again, just alkene stability trends is what's important here, more so than the radicals. Feel free to stop me if anything doesn't make sense. Otherwise, I'll assume you guys are all on the same page as me. It's not the best cyclohexane. Okay, so here we have this position, and this position. These are all alike, they're right next to the double bond. So there's going to be a lot of products, but I'll go ahead and show all of them. So first, I'll just draw the products from like just adding bromine to the allylic position. So there's that. There's this. And I'm going to kind of squeeze this one in. And if you were to name all of these, they would have different names. So like this would be, well, no, I'm not gonna do that unless you guys really want me to, but if you were to name these, you'd find they have different names that are all different molecules. So like the bromine up here and the bromine down here, you have different products. And the methyl group is kind of why, because it gives a sort of shape to the molecule. Okay, so now we can look at the allylic intermediates and their resonance forms to see what other products form. So here's one. There's the resonance form. Oh, it's not correct. So the double bond is here, and the radical is here. And if the halogen added to this radical, then you get this product and other intermediates. I'm gonna go ahead and circle the products, at least a little bit like I did before. So another intermediates there is this one down here. And I'm pointing to the carbon with the methyl group there for where that radical is going. So now the double bond is here, and the radical formed is here, and then that will lead to this halogen. And one last intermediate is this one here. So I'm going through this quickly because resonance is something we covered before, and I covered it last week, and I'm assuming you guys are comfortable. So this is a radical that forms from this resonance, and then this halogen would form. So there are 6 different products that form from this. Now to determine the most stable one, again, we'll look at alkane stability first. So for all three of these ones at the top, we have free substituents on the double bond, so it's tri-substituted. Now this one here has also free substituents, so that's also tri-substituted. This one has two substituents, so it's di-substituted, and this one also has two, so it's di-substituted. Okay, so there are four that have free substituents, and all four of those, well, actually, so it's going to be a bit hard to show, but I guess I'll box them. So this formed from a secondary radical, as well as this one and this one. So I'm sorry, you know, it's kind of cluttered. It's hard to make space with this whiteboard, but the ones that I boxed are the major products because they're tri-substituted. So those are the most stable alkenes, and they formed from secondary radicals because they're at secondary carbons, like this carbon here is secondary, and those are too. And then this one here is primary. So the primary radical is less stable than a secondary radical, so that was a less stable product, and yeah, that would form less than the secondary radical ones. So again, the boxed things are the major products, and hopefully my explanation makes sense. Alrighty. And then the last part, 2D, 2D, that's what I'm looking at. So this is technically allylic, and so is this, like this position on the left is right next to a double bond, as well as this position on the right. But this position on the right has two hydrogens on it, while this one on the left has no hydrogens. This carbon here is, like, its octet is happy with everything we can see here. There's three carbons over here and another one over here, so that carbon in the middle is fine. Doesn't have any hydrogens, and you kind of need a hydrogen to abstract to form a radical in an intermediate, as an intermediate in like a propagation step that leads to that brominated product. So because of that, there's not going to be any bromine added over here. So I guess we'll just show that with this because there's no hydrogen there to lead to a radical to lead to the bromine getting added there. So that's sort of a red herring in this problem, I guess. But over here on the right, everything is the same as it has been. So products that can form at the allylic position is just this product. And then if we want to look at the intermediates that led to that product, we have a radical here. And that resonance form puts the double bond here. Nope, that's where it was before. Puts the double bond here and the radical here. And then that will lead to a product with the halogen where the radical is, like this. Okay, so again, let's look at the stability of the alkenes. This one has two substituents, so it's di-substituted. And this one also has two substituents, so it's di-substituted. And then both of these positions with the bromine are secondary. So as far as I can tell, they're both equally stable, so there's not really a major product. They probably form in close to equal amounts, so I'll just circle both of them and say that both are major products. There might be some slight difference between the two, but it's so small that you wouldn't be expected to recognize it on a question, probably. So that was number 2. Number 3 is just ranking the stability of radicals, which is something we've kind of been doing already today. So, like I've been saying today, the more substituents the radical has, the more stable it is. It's the same pattern as carbocations that you guys saw earlier. Yeah, that's correct, Franklin. So like if we're comparing this cation on the left to this cation on the right, this cation is tertiary and this one is secondary. So the tertiary one is more stable than the secondary one because it has more substituents. And the radicals follow the same pattern. The more substituents it has, the more stable it is. So a tertiary radical is more stable than a secondary radical, which is more stable than a primary radical. That's why the order is 1, 3, 2, like this. And for part B, okay, so we can look at the substituent number on all of these to start. So this first one, the carbon that the radical is on has 2 substituents here and here. So it's secondary. The second one has 3 substituents on the carbon of the radical, so it's tertiary. And then this one has 2 substituents, so it's secondary. So both this first one and the third one are secondary radicals, but is the stability for these two the same? The radical doesn't look like much of a radical, but are these two equally stable, or is there a difference between these two even though they're both secondary? Does anybody know? Is there anything important about this radical that I didn't point out? It's right next to this double bond. So this radical is allylic, yes. Thank you. So not just the number of substituents, but also like what the surroundings of the radical is important. If a radical is right next to a double bond, it's allylic and it's more stable because of resonance, which is something we've covered on the last worksheet. Resonance makes things stable, and this has a resonance form like this. I'm going to erase to avoid clutter, but that's what it looks like. Alkene stability, radical stability, and then allylic. I think I understand where your question is coming from, but like for number 2, I was talking about the major products, and the alkene stability was more important than the radical stability because the alkene stays in the product, like the radical's gone once you get to the product. So I believe the stability of the alkene is more important for determining what forms the most. But like in terms of a stability trend, like for number 3, I'm just asking to rank the stability of the radicals. So we're just looking at the radicals and the alkenes are all the same here. But the trend is something like, you get it, but I'll still go ahead and say it as like, so like from left to right, this is increasing stability for radicals. It doesn't look like it's E. My bad. So like a methyl radical is less stable than primary, which is less stable than secondary, just tertiary, allylic, benzylic. So like this one I pointed out is allylic, and benzylic, like we saw last week, would just be something like this. It's right next to a benzene ring, so it has like 5 resonance forms, so it's even more stable than an allylic radical. Just an FYI. So yeah, if we use this stability trend going from left to right, we can determine what is the most stable. I wouldn't really recommend like memorizing this sort of graphic, but you should understand that like substitution is important, but things like the double bond or a benzene ring are more important than substitution. Like a primary allylic radical is more stable than a tertiary radical that's not allylic, so this takes precedence. So this secondary allylic is the most stable, and then now we're looking at substitution only, so tertiary is more stable than the secondary. So it's 1, 2, 3 for the stability of these. And if I were to add this, which I don't think he went over, but I'll cover it just as an FYI. If you were to guess where this last one would fall on the stability, where do you think it would go? Like what number should I give it? With like 1 being more stable and 4 being less stable. So I'm pretty sure it would be less stable than a methyl. I'm not positive, but this is, I'm pretty sure, called vinylic when it's on the double bond, because this carbon with the radical is also in the double bond, and it isn't happy to be there. So a vinylic radical or a vinylic carbocation is generally very unstable and don't form. So this would be the least stable if this was part of the question. If you didn't cover that in class, don't worry about it, but just, I figured I'd cover it as an FYI, because it might come up next semester, if anything. Okay. So can anybody tell me what these conditions do? Like what the product will look like, or what the product is called? We have an alcohol reacting with PBr3 and THF. THF could also just be written as ether, because they're both ether solvents. So think you'll cover the mechanism for this next time, but you should know from last lecture on Thursday that an alcohol with PBr free will substitute a bromine for the alcohol. So just substitutes a bromine there. And there are some byproducts here that I doubt he expects you to memorize those, because that's not what we care about. We care about this substituted product. You get rid of the byproducts, then you isolate this anyway. So yeah, alcohol with PBr free in an ether solvent leads to substituted alkyl halide, or alkyl bromide in this case, with PBr free. And this is good for primary and secondary alcohols. And that will be important coming up in your next lecture, probably, but just so you know, this is what these conditions are good for. Okay. Moving on to 4B. This was probably kind of loud. So now we have an alcohol with SOCl2 and pyridine. Does anybody remember what these conditions lead to? What product would form? It's nearly identical to the last reaction with PBr free. The only real difference is we have a chlorine instead of a bromine, so we'll form an alkyl chloride. Substitute the Cl for the OH, and again, there'd be some byproducts, but this is all you care about. And just like with PBr free, this is generally good for primary and secondary alcohols, as you will see on Thursday. Again, if anything I'm covering you don't understand, feel free to stop me, but this is just a reaction that you'll have to know if you don't remember it. This and PBr free are both important. Now we have an alcohol reacting with hydrochloric acid in an ether solvent. Does anybody know what this will lead to? So it will be basically the same product as what we saw in part B. It'll substitute a chlorine for the alcohol, like this. And this is a mechanism that makes a lot more sense than the SOCl2 and the PBr free mechanisms. So I think I'm just going to go ahead and show it to you, and you'll hopefully see it on Thursday. This is a pretty general mechanism that applies to multiple reactions. So I'm going to erase the board so I can just give myself more space. But I'm going to be looking at the same thing. So the THF is just a solvent. It's not really going to interact in the mechanism. But as we know, oxygen is electronegative. It has lone pairs, so it can act as a nucleophile, and HCl or HBr can act as an electrophile because of this dipole. So the oxygen can attack the hydrogen there like this, very similar to like when we had double bonds attacking the hydrogen and leaving a Cl minus. It's just the oxygen being the nucleophile instead of an alkene. So then we have this positively charged water intermediate. And then it's positive, so it doesn't want to stay there. So it just leaves by itself. And then we get a carbocation here. And obviously the carbon doesn't want to stay negative. I mean, it doesn't want to stay positive. And we formed a negative chlorine at the beginning. So the chlorine will act as a nucleophile and attack the carbocation, which is an electrophile. And it leads to, that doesn't look great, but it leads to this product with the chlorine on the same position as the alcohol was. And I'm getting ahead of your lecture, but you'll see this soon. This general mechanism is the SN1 mechanism. So it applies to any SN1 reaction. It looks basically the same. It's just a different leaving group and a different nucleophile. But it's the same steps every time. So if you have any questions about this mechanism, it'd be good to ask. But if you understand it, that's good, because that's a pretty big portion of what you need to understand for your next test. Yeah, I'm not going to get more detail than that because I'm ahead of your lecture, but hopefully that made sense. So we have an alkyl halide. In this case, it's bromine reacting with magnesium in an ether solvent. Do any of you know what the product of this is? So I'll just draw the skeleton because that's generally not changing. Carbons are going to stay where they were before. Like always, the ether is just a solvent. It's not going to really do anything in terms of the reaction. Okay, so this magnesium here, you don't have to know the mechanism or how this happens. You just have to know that it happens. It basically just shoves itself in between this carbon here and the bromine here. So that doesn't look amazing. You get the carbon bonded to magnesium, and the magnesium is bonded to the bromine. So that's the product. And you might recall that he said that this is a Grignard reagent. So I could see a potential multiple choice question being like, what conditions with an alkyl halide lead to a Grignard reagent, and then magnesium and ether. And in order to answer that, you'd have to know what a Grignard reagent is, which is this, a carbon bonded to magnesium, which is bonded to a bromine. So it's good to know like lingo, like what this is, how you formed it, what it looks like, all that stuff. And The next question, number 5, asks if the product from 4D will behave as a nucleophile, electrophile, or both. So like here with the alkyl halide, guys hopefully easily recognize that we have this dipole between the carbon and the bromine, because the bromine is more electronegative than the carbon. So the bromine has a partial negative and the carbon has a partial positive. But if we look at a periodic table, magnesium, I'll just draw a little sketch. To be honest, I don't remember exactly where magnesium is off the top of my head, but I mean, we know carbon is up here and magnesium is a metal, so it's going to be somewhere to the left. I'm not going to put a specific area because I honestly don't remember, but it's somewhere to the left. And electronegativity, yeah. All that's important is it's less electronegative than carbon because electronegativity increases going to the right and going up, and magnesium is somewhere to the left and going down. So this is like increasing electronegativity. Magnesium somewhere over here, so it's less electronegative than carbon. So this is what the dipole between magnesium and carbon looks like. There's a partial negative on the carbon and a partial positive on the magnesium. There's also a dipole between the magnesium and the bromine, but that's not as important in terms of reactions. But this dipole giving the negative charge to the carbon is important, so it can technically act as both, but the Grignard reagent generally acts as a nucleophile. And carbon acts as a nucleophile, and you're not going to see much of that this semester, but you'll see a lot of it next semester, so just try to remember this, even though it's not going to come up much on your test. At most, he'll probably ask how to form it. Okay. Number 6 is, go ahead and draw this. So this probably could happen, but it would be very slow, like I said in number 6, the instructions. So he probably didn't cover it, but I showed you guys the mechanism for this, and I'm gonna go ahead and go over it again. But while I'm going over it, if anybody, like if a light bulb goes off in your head and you want to say explain why this would be slow, feel free to do so. That way I know you guys are understanding. Just like with 4C, it's the same reaction with an alcohol and hydrochloric acid. So this is the first step in the mechanism. We form water, and it has a positive charge as an intermediate, and the water doesn't want to be positive, so it just leaves the carbon. We have a carbocation here, and then the negative chlorine will attack that carbocation and lead to that product. So what's important here to note is this step. This step has a carbocation as an intermediate, and this carbocation is on this carbon. It's only bonded to one other carbon, so it is a primary cation. And our primary cation is very stable. Can anybody say like yes or no? Are they stable? No, they're not very stable. They're pretty much the most unstable cations. So this intermediate would probably form pretty slowly. And because this intermediate would form pretty slowly, the chlorine wouldn't be able to attack it very easily. So this product wouldn't form very quickly. And that would slow the reaction down because of the substitution of this cation. If the alcohol was instead here, then we'd get a tertiary cation. And then the reaction would probably go pretty quickly because the tertiary cation would form pretty quickly. And there is a potential for like a hydride shift towards that tertiary position, but like this leaving group probably wouldn't leave like that to form the cation very quickly, so it would still be relatively slow. So the stability of the primary cation is why this reaction with hydrochloric acid or hydrobromic acid on a primary alcohol doesn't work very well because of this intermediate. So intermediate forms slow. Okay, so hopefully that makes sense. I'm gonna erase that bottom portion with the mechanism. It doesn't look like anybody's checked on. Okay. So what would be good, like we can still get from this alcohol to this alkyl halide. We just have to use the other conditions for adding or for substituting a chlorine for an alcohol. Can anybody tell me what those conditions are? It came up in question 4. We had PBr free with THF to add a bromine. And we had SOCl2 and pyridine to add a chlorine. So like I noted before, this is good for primary and secondary alcohols. And that has to do with the mechanism it goes through, which you'll see in lecture. And then HCl or HBr to substitute a halide for the alcohol is good for tertiary alcohols because it passes through that cation intermediate. So hopefully at least the pattern for what HCl is good for makes sense because I've shown you the mechanism. Right. Can anyone tell me what the conditions are to get from, I guess, 1 to 2? While I finish filling out the rest of the intermediate steps. That's really close. Yeah, no, it's good that you guessed. I appreciate it. And like I've said before, like I learned the most from this class by guessing and being wrong. So like you were on the right track because the oxymercuration, yeah, it's easy to mix the two up. What Jared suggested with oxymercuration, that leads to Markovnikov alcohol. And if we look at this double bond, this position is tertiary or tri-substituted, and this one is secondary. And we want to add it to the secondary position, so we want the anti-Markovnikov. And in that case, like we do the hydroboration reaction, which is 2 steps. The first step is just BH3 and some ether solvent. And the second step uses hydrogen peroxide, which is H2O2 and a base. And that gives the anti-Markovnikov alcohol. So that's the first one. Okay, what about going from this alcohol to the alkyl bromide? And step 3, what conditions can lead to that? So when it's secondary, and this is secondary alkyl halide, both conditions for adding the bromine are kind of equally valid. If it's secondary, it's generally better to use this PBr3 and THF, but because it's secondary, doing this is pretty much equally valid. So either of these, PBr3 and ether, or hydrobromic acid and ether, would be okay to substitute a bromine for that alcohol. And then this last step, going from 3 to 4, we're forming the Grignard reagent. That's what this is. Because we shoved the magnesium in between the carbon and the halide. And what conditions can form a Grignard reagent? Magnesium, yeah. The solvent here is actually very important. It has to be THF or an ether solvent. Like, a lot of the time, they're kind of just suggestions. Like, here, a different solvent would work for this. It might be slower than it would be in an ether solvent, but it would still work. But when you're doing the Grignard reaction, this has to be an ether solvent. So that's just something to take note of. If you didn't emphasize it, it's probably not a big deal, but that is true. It has to be an ether solvent. So it might be something to note down just in case it comes up as a multiple choice question or something. Okay. And the last problem, number 8. That's parentheses. I shouldn't have put a comma there. But these are parentheses around this. And that's in THF. So it's just CH3, CH2, and then there's 2 of them, CuLi and THF. I think you guys finished covering this in class today. So what does this lead to? Like, what kind of product forms? In the reagent, we have 4 carbons. Are we going to have 4 carbons in the product? Or are we going to add more or take away some? What's the difference between these? So those conditions are what lead to this. So like, it's I'll just take this as an example. You reacted an alkyl halide with lithium and then with copper iodide in an ether solvent. You would get this, which is similar to what we have here on top of the arrow. So these are the conditions you use to react with an alkyl halide in order to form this, and this is called a Gilman. I might spell it slightly incorrectly, but it's called Gilman's reagent. That's what this is. And then you can take a Gilman's reagent and react it with the same or a different alkyl halide to do what the reaction we're looking at here. But does that explain the difference? Like, what you brought up is how you form this copper complex, and then you use that same thing to react with an alkyl halide with these conditions. I know it's a bit weird because it kind of seems like it's going in a circle, but it's just how this is. So I'll go ahead, erase this just a little bit. So what I have in parentheses there is basically just like this to an extent. Well, that is what it is because it's CH3, CH2, so those are just ethyl groups, and it says there are two of them bonded to the copper. And I'm pretty sure the lithium is just a counter ion, so it's probably just floating around or something, but don't usually draw it in these. So are we going to add just one ethyl group, or are we going to add both of them? Because I guess this is something you should know, like these reactions add carbons, they form carbon-carbon bonds. You don't really have to know the mechanism, but you have to know, like, they add carbons, and you should know how many they add. Okay, so it's only going to add one. So even though there's two ethyl groups here, it's only going to add one ethyl group. So we're just going to add 2 carbons, and they're basically going to take the place of that alkyl halide. So the bromine's going to go away, and a new carbon-carbon bond is going to form where that bromine is. So here's the skeleton, and then that's where the bromine is. Now it's bonded to a carbon and another carbon because we added an ethyl group. So that's the product. So when you react an alkyl halide with a Gilman's reagent, which is this copper complex with some carbons and ether, it just forms a carbon-carbon bond where an alkyl halide was. And this is more than likely going to come up on an exam because reactions to form carbon-carbon bonds are kind of important, so I'll probably ask about it. So it would be good to at least like recognize this reaction. Yeah, that's good. Okay. Be able to draw products when you're given these reagents. So I apologize, my parentheses generally don't look very good, but this is CH3 parentheses CH2 and then 4 outside parentheses. And then the closing parentheses around all of that, there's 2 of them. So this is another organometallic coupling reaction with the Gilman reagent. And the Gilman reagent here is just like we have 1 carbon with the CH3 and then 4 carbons with the CH2s there. So there's 5 carbons total. So 5 carbons onto 2 copper. It looks something like this, probably. It's just 2 pentanes attached to the copper complex. So we can take one of those pentanes and kind of just shove it in where that bromine is. Like, the mechanism is not anything like this, probably, but I'm just drawing these arrows to show like what happens. It takes the place of the alkyl halide, just like it did before. So I'll draw the products down here. I just added 5 carbons. At least I think I did. I'll count my carbons to make sure I did, and that's always a good idea. So we had 1, 2, 3, 4, 5, 6 in the reagent, and we added 5, so we should have 11 in the product. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So yeah, I added the correct number of carbons. I know that seems like a silly thing to do, but you'd be surprised how often people count incorrectly. They add 1 too many or 1 too few. That's obviously not correct, so it's a good habit to make. And last part. I have a hard time doing this in ChemDraw, but this is generally how no, I probably shouldn't do it like that. I'll just keep it the way it is. I don't think he'll ask something like this. I was just trying to come up with a semi-more complicated Gilman reagent, but it'll probably be something like a methyl group, an ethyl group, a propyl group. The most complicated it would get is probably like something like this, like 2 of these being added, but I don't know if you'd even do that because it can be confusing, like what carbon you're attaching where the alkyl halide was. But like here, these 3 carbons at the end are all the same, so there's not too much confusion, I think. And the Gilman reagent would look something like this. So we're just adding one of these guys, which is a isobutyl, if you want to know what the name of this is, but you don't really have to know that too much right now. It's just nomenclature. But we're adding one of these isobutyls here, kind of, again, not the mechanism, but I'm showing like what kind of happens. So that's the product that would form. And again, it's good to count the carbons to make sure we didn't add too many or too few. So there are 6 up here. There are 4 carbons in the reagent, so we should have 10 in the product. There's 5, 6, 7, 8, 9, 10. So that's correct. And I feel like with something like this, it might have been easy to draw this as the product. But again, like if you counted the carbons, you'd notice that's incorrect because this has 5, 6, 7, 8, 9. So we didn't add 4 carbons like we should have because that's how many were in the reagent. So that would be a sign that was done incorrectly. I point that out because I actually did that at first, so I wouldn't be surprised if that's a mistake somebody else made. So, did all these Gilman reactions, the organometallic coupling, make sense? Because there's a good chance it'll come up. And I'm hoping this practice has helped you guys become comfortable with it. I don't have anything else on my worksheets. I'll probably go a bit ahead of your lecture with my next worksheet just because I don't want to be too far behind by the time we get to the exam. So yeah, I'll let you guys know when that's up. You can start looking at the worksheet. If there are no questions, yeah, no problem. I guess there are no questions, so I'll go ahead and end the recording.